So hopefully the last example got you thinking about the difference between mean and standard deviation and what they tell you about data. On this slide, I also want to show you what mean and standard deviation look like. And in the class survey, I used to ask about height. I stopped a couple of years ago when I realized it might make people who are either very tall or very short feel singled out because it's a visible thing. But in any case, this is height data from the class a couple years ago. And I have the height split up for men in the class and women in the class. And it's height in inches. So what you can see is that on average, the men in the class had a height of 68.1 inches, and the women in the class had a height of 63.9 inches. So on average, the men in the class were taller than the women in the class. And this is reflected in the fact that if you look at the x-axis on both graphs, the bars for the men in the class are centered around a higher height than the bars for the women in the class, which are centered around a lower height. What you might also notice about these graphs is that the graph for the men is much more spread out than the graph for the women, which is much more clustered together. And here what you're seeing is differences in the standard deviation. And the standard deviation for men in the class was 6.22, while the standard deviation for women in the class was 2.44. And so for men in the class, the average distance between each value of height that was given and that mean of 68.1 was 6.22. So that's how spread out they are from that mean. For the women in the class, the standard deviation of 2.44 meant that the average distance between women's heights and that mean of 63.9 was only 2.44 inches. And that's reflected in the fact that the graph is more tightly clustered around the standard deviation. So when you have a big standard deviation, you have a fat spread out graph, and when you have a small standard deviation, you have a more narrow graph that is more clustered, more tightly clustered around the mean. So that's all I have to say about the standard deviation. And I'm going to end this unit now with a brief discussion of what descriptive statistics are. And you might have heard me talk about descriptive statistics in the class before. I definitely said descriptive statistics earlier in this lecture. And what descriptive statistics are any statistics that describe the data in a sample or population. So if you're looking at some set of data and you are calculating a statistic to describe that specific set of data, you have a descriptive statistic. By this definition, everything we've covered in the class so far has fallen under the category of descriptive statistics. So every single thing we've done so far has been descriptive statistics. That includes frequency tables, that includes all measures of central tendency, and that includes all measures of variability. And so at this point in the class, you now have a pretty good grounding in how to find descriptive statistics for samples and populations at different levels of measurement, and you know lots of different ways to describe data in a sample or population. In an in-person semester, this would be the point at which we have our first test. In this semester, this is just the point at which I say, congratulations, you know some stuff about descriptive statistics. And when we come back next week, we'll be talking about different types of statistics and different statistical applications that will move away from just describing what's in a sample or population. But until then, don't worry about that, and just be glad that we have reached the end of our unit on descriptive statistics. And so the last topic for today is going to be a brief overview of statistical software, and more importantly, what you can do with it. And we'll be focusing on using statistical software to calculate several of the descriptive statistics that we've been talking about in this class so far. And so I want to start out this part of the lecture by just noting that there are various types of statistical software out there. You can find many statistics using a program like Excel or Google Sheets. There are some statistical software programs that are very, very complex and are only used for high-level statistics, and there's pretty much everything in between. In this particular class, I don't care that much that you know the names of different kinds of statistical software, or even that you know how to use any particular kind of statistical software. This is because when it comes to learning software, pretty much anybody can learn how to input the right commands and get an answer out. And that's a different sort of learning than what we're doing in this class. In this class, I'm much more concerned with your ability to interpret the statistics that come out of it, which is why we spend so much time learning the hows, whats, and whys of statistics and calculating them by hand, and relatively less time talking about statistical software. So as I go through these examples, I'm going to be showing examples from one particular software package called Stata, which just happens to be what I use. It's not necessarily because this is the most important statistical software package or because I want you to know anything about Stata in particular. But what I want you to be thinking about is just A, the fact that there exists statistical software, and B, how to interpret the different kinds of things that it might spit out. In order to talk about statistical software, though, I have to talk about something that's common to every kind of stats program out there, which is variable coding. And when you're working with statistical software, you generally want your variables to be coded as numbers. In other words, we're going to assign codes, which are defined as numerical values that you can assign to different variable attributes just for the purposes of storing them or analyzing them in a statistical software program. So again, when we talk about variable coding, we're talking about assigning numerical values to different values that a variable can take on. When defined this way, variables at any level of measurement can be coded numerically. And here are some examples of what coding might actually look like. If you had a variable for gender, you might code female as 1 and male as 0. So in this case, you'd be assigning the numbers 1 and 0 to these different variable attributes. Another variable that might be coded would be one that measured happiness on a scale from very sad to somewhat happy to very happy. And so this would be an ordinal level variable, where we have different categories of happiness and sadness that are in order from least to most. Typically, when you have an ordinal variable, you just assign numbers to them in the order that the categories appear. So here you could code it 1 equals very sad, 2 equals somewhat sad, 3 equals somewhat happy, and 4 equals very happy. An exam grade would be an example of an interval level variable. And in examples like this, it would be common to just assign numerical values to the corresponding numerical values in your variable. So you'd code 100% as 100, 90% as 90, and so on. And so what you can see here is that the common theme in all these things is that we're assigning numbers to the different attributes that variables can take on, even for variables that are measured in different ways. And then finally, if you're looking at ratio level variables, they typically tend to be numerical anyway, so you don't have to do a whole lot there, but 0 might equal 0 dogs in a variable of number of dogs owned, 1 would be 1 dog, 2 would be 2 dogs, and so on. With those variables that I just talked about, you might end up with a data set that looks like this. And so each case would be each particular member of a sample. So if you remember, a case is just a single member of a sample. And then for each case, you'd have different numerical values input depending on how you coded the variables. And so in that first row there, case number 1, where we're measuring gender as female equals 1, male equals 0, this would be somebody who's said that they were female. On our scale of happiness, from very unhappy to very happy, this person would be very happy because 4 was coded as very happy. They would have received a 90% on their exam, and they would have no dogs. As another example, we have case number 3 there. Their gender is coded as 0, which would correspond to male. Their happiness level is somewhat happy. And they received a 30% score on their exam for that 30 there under grade, and they own 7 dogs. So the 7 corresponds to that. So this is how variable coding works. And as I said before, variables are coded like this for the purposes of storing them and analyzing them in statistical programs. And as a quick note, once data is coded, sometimes ordinal and other non-numerical variables are treated as numerical. So for example, you could find the mean level of happiness here based on these 1s, 2s, 3s, and 4s. And the important thing, if you're doing this, is just to remember what the statistics actually mean. So a mean level of happiness of 1.2 here would mean that your average level of happiness is somewhere between very unhappy and somewhat unhappy. That's not actually what the average is. I didn't calculate this before saying that. But my point is that when variables that are not numerical are coded numerically, you can find statistics for them that you could find for any numerical data. But the most important thing is just to remember what the statistics actually mean and make sure that you're interpreting them in reasonable ways. And in this class, I'm generally not going to have you do that, but that is something that you'll see in published research and in other places. And it's good to always just keep in mind, though, what that underlying meaning of the variable is. So with this, I'm going to show you again the data from our class survey. And this is what I put up in that first lecture about frequency tables and said, it's really hard to take a look at this and have any idea what's going on. Hopefully at this point now you have slightly more of a sense for what this is showing us. And as you can see, this is the exact same format as the table I just put up on the last slide, where on the left-hand side we have numbers, and those are different cases or different members of the class who took the survey. And then I have all these different variables here that are coded numerically in different ways. And if you squint, for example, you can see that first column is labeled death P, which is the support for the death penalty variable. And it's coded as 1s and 2s, where people who said that they support the death penalty are coded as 1, people who said that they oppose the death penalty are coded as 2. And so with each of the different variables in here, you can see that they're all coded with different numerical values. And once you have data that's coded that way, you can have a statistical program do all sorts of things for you much, much more quickly than you can do them by hand. And so in reality, if you're not taking a statistics class, almost everything you do with statistics is going to be done in some sort of statistical software, and it's going to take about 5 seconds to get to all these different values that I've been having you do by hand. The reason I have you do them by hand, of course, is that I want you to know where they come from, know what they mean, and know how to interpret what's coming up when you use the commands in a software program. So the next couple of slides, I'm going to show you examples of how the statistical software can be used. Again, the particular software that I'm using here is called Stata, but there are many kinds out there. This is just one example of them. So if you're working with Stata and you want to find a frequency table, you would use a command called tab. And to demonstrate this, I'm going to use that variable asking whether you had ever been in a physical fight. And so this was one of the first examples that I put up there for frequency tables, and I'm going to show you how it comes up when you find a frequency table in this program. You say tab fight, so that's saying find a frequency table for this variable named fight. And what it pops out is pretty similar to a frequency table that you would make by hand. The main difference is that instead of seeing the variable attributes named, you see the numerical codes that are assigned. So here, yes and no are coded in the same way that they were for the death penalty, where yes, I've been in a fight is coded as 1, and no, I haven't been in a fight is coded as 2. So this gives us the same information that we got from frequency tables a couple weeks ago, where you can see that in our class, 29 people have been in a fight and 24 people have not been in a fight. So we have the variable name and the different values that are coded to correspond to different variable attributes. You have the frequencies, and here you have relative frequencies as well. Another example of using software to find a frequency table would be for the variable asking about number of times you've been stopped by the police, which was coded numerically. And here, even though my head is covering a little bit of it, you can see a similar frequency table where you have the numbers of stops, the frequencies, and then you also have relative frequencies and cumulative frequencies in that last column there. So software can be used to find frequency tables, and that's how you would interpret what's shown in these frequency tables. You can also use statistical software to find descriptive statistics like mean and standard deviation. And the particular command that I'm showing here is called sum, but again, I really don't care that much that you know the specifics of any particular program, because if you end up working somewhere and they want you to do statistics, chances are you'll be working with whatever software they happen to have. So you'd want to learn the commands and just know what it is that they're telling you. So here's the same variable again, asking about police stops. And here we're going to use this command sum, and it pops out output that looks like this. So if you were working with this particular program, it would show you your total number of observations, or n. It would show you this mean of 1.615 stops, which you might remember is what we calculated for the class by hand as well. Or sorry, by just showing the data as well. You can also see the standard deviation for this variable. So the standard deviation for number of stops in the class is about 1.6 if you round. So that's saying that's the average deviation in number of stops away from this mean of 1.615. And then this command also happens to pop out the highest and lowest values as well. Also showing an example of this for the variable a in the class, which shows the total number of observations, the mean, so how likely do you think it is you'll get an A in the class? We had a mean of 80. The standard deviation, which was 22.5 points, and then also the highest and lowest values as well. And for all these, if my head is covering them, keep in mind that there are now PDFs of the PowerPoints in each module as well. You can also find the median using statistical software. And again, although the command is less important than being able to just look at output for a program and interpret what's going on there, you get output that looks like this. And this one's a little bit weird looking. It doesn't say median anywhere, but where you find the median is this value that's listed for the 50th percentile. And that tells you 50% of the values are smaller and 50% of the values are larger than this value of 1. And if you remember, we had a median of 1 for the stop variable, so that's what that's telling us. This also gives us other information as well, such as the total number of observations, the mean, the standard deviation, and the variance here, as well as some other statistics that we did not cover in this class. So that's the end of your crash course in statistical software. Again, what I want you to take away from that is that A, the software exists, and if you're ever in a job that asks you to do statistics, you'll be working with some kind of software. And B, I want you to just practice reading statistical output and understanding what it means in the terms that we've learned earlier in the class in examples that we've done by hand. That's the last part of the lecture, so I'll just end with my usual couple of quick reminders. Problem set 4 is due this Sunday at 11:59 p.m. as usual. The optional review session will take place from 2:30 to 3:30 on Wednesday, or at an alternate time if you want to just meet with me, that's also good. And if you have any other questions that you don't want to deal with in a meeting, you can either comment on Canvas, which is nice because everybody can see it, or feel free to just email me with any questions that you might have. And otherwise, have a great week.